So, many of you came up to me in the break and talked about the parameters and what are these psi t's, kappa t's, how do you tune them and so on and so forth. And that's exactly the same kind of questions that I had when we were looking at these bundle methods and said, oh my god, these are, this is god awful amount of engineering goes into doing all these kind of things, right. So, can we actually do something better? So, what we want is we do not want to do this null step serious step business, we do not want to tune these parameters, right. Now, if I give you a black box objective function, right, which is non-smooth and convex, then more or less you cannot avoid this, right. But again, in machine learning, we know a lot. We know that the objective function that we are evaluating or the function that we are minimizing has the following form. There is a regularizer, there is a risk, and so on and so forth. So, can we do something better? Can we try to adapt these bundle methods in a way that you get rid of some of these pain points? Okay, so that's what we were looking for, and turns out here is the really obvious straightforward scheme, okay, to do this. Okay, so before you get lost in the equations, let me guide you through them a little bit. Okay, so the intuition behind what we are doing here is that you say, what is a regularizer, right? So, if you think about it for some time, the regularizer in machine learning is a stabilizer, right? And if you think about here, what did we add? We added a stabilizer, right? So, we did a cutting plane method, we added a stabilizer, okay? And the other thing that happens in machine learning is more or less the regularizer is usually not is usually differentiable, okay. It is not always the case, but it is usually differentiable. So, if you take L1 it is not the case, but say if you take L2 or entropy or any of the other regularizers, they are differentiable, okay. So, the regularizer is sort of exactly the thing that you need for stabilizing your model, but the regularizer in machine learning is also exactly stabilizing your objective function in some sense, okay. And usually you would see this is the case that the empirical risk is the non-smooth part. I mean, this is where most of the pain point is, because the empirical risk turns out to be non-smooth. Like for instance, in the hinge loss, if you use the hinge loss, then this summation is a summation over max of 0 and something, and that one is clearly non-smooth, okay. So, the pain point usually is that the empirical risk is non-smooth, while this guy, the regularizer, is usually smooth. So, here is the dumb straightforward idea, is to say, why do not we take the empirical risk and build a piecewise linear lower bound for that. So, in other words, we only build a piecewise lower bound, linear lower bound, a cutting plane model for the empirical risk, okay. We do not touch the regularizer, and then every iteration we add the regularizer back to the cutting plane model of the risk and then minimize it, okay. And then we keep doing this until we reach our tolerance. Really, really simple, nothing complicated at all, okay. One thing to notice here, no parameters, nothing to tune, okay. You give me your epsilon and I happily chug along, no psi, no kappa, no nothing, okay. Sort of seems magical. It turns out that you can prove this is not just magical, but this is actually provably converging, and it is provably converging at rates that are better than normal bundle methods, okay. So, how does this work, okay. So, before you balk at this whole slide with tons of equations, look at this, okay. By the way, this is where your condition number enters the picture, because you have you need to ensure that the norm of your second derivatives is bounded, and you need to ensure that your gradients are bounded. Both of these are pretty standard assumptions, and you will see that there is a linear dependence. So, the H enters the bounds, okay. So, what happens is that the way to navigate this beast is to understand that this is a constant, okay. This is more or less depends on where you start from, it depends on the condition number of your problem, what value of lambda you are using, and the bound on your gradients, but this is a constant and it has a log dependence, very mild, okay. That is again a constant. The term, the dominant term that you are working with is this term. What this tells you is that if you want epsilon precision out of this simple algorithm that I described, oh, by the way, I forgot to name the algorithm, we call it bundle methods for regularized risk minimization, which is short for BMRM. Okay. So, it turns out that if you use that simple scheme that I showed you, BMRM will converge in order 1 over epsilon iterations to an epsilon accurate solution. Okay, so, this is the dominant term, this is the only term that you need to pay attention to, and you get order 1 over epsilon rates of convergence. Okay, for if your objective function satisfies some benign conditions. If furthermore I tell you a little bit more about the objective function, I not only tell you that you are minimizing a regularized risk, but that regularized risk is actually smooth, and not just smooth, but again the norm of the Hessian is bounded in a certain way, then the dominant term becomes log 1 over epsilon. So, in other words, to get an epsilon precision solution, all I need to do is take log 1 or order log 1 over epsilon steps, and I am done. Okay. This proof looks very ugly and sort of the constants look really awkward, but let me nevertheless be brave and try to walk you through the proof. Okay. It is not because I want to put you back to sleep right at 9:30 in the morning, but because it is a very intuitive proof, which the basic idea behind this proof appears many times in machine learning, and actually in fact this very proof has been discovered 2 or 3 times at least in machine learning before. Okay. So, in various forms. So, the way you do this, before we again get lost in the math, the basic idea behind the proof is the following. You show that whatever is the objective function that you are minimizing, this piecewise linear objective function that you are minimizing, and then you have a regularizer. So, here for simplicity I am only going to do with the square norm just because it is really simple. If you have a square norm regularizer plus your piecewise linear lower bound for your empirical risk, and you look at the dual, okay, you can say something very nice about the dual. In this case you can say that the dual to this problem, so this is the problem we are solving at every iteration, remember. Okay. The dual to this problem turns out to be a quadratic programming problem. Okay. Again, if we have time, when we go through the 5th lecture, I will actually derive something very similar to this in the context of SVMs. Okay. So, this is more or less very similar to what you would see in an SVM setting, if you remember, and then this is sort of the dual. So, some of you who know SVMs already, this should be fairly familiar. This is the kernel matrix, and then you have some constraints on the alphas. So, you get a dual which is basically a quadratic program which has a quadratic objective and some linear constraints. Okay. Now, because you have strong duality, so Dale mentioned this before, the objective function value for the primal and the dual are exactly the same. So, if you minimize the primal or you maximize the dual, they are one and the same. The value that you would get is exactly the same. Okay. And now what you can do is you can take this quadratic objective function that you have in the dual, and you can sort of say, instead of minimizing it over all variables alpha, how about if I really be cheap and only minimize it with respect to one variable. So, in other words, I keep all my other variables fixed, just move one variable. Again, this is very similar to coordinate descent that we saw before. The same idea we will come back to again when we do, if we have time, and we do the coordinate descent in the dual for SVMs, then we will come back to this again. Okay, but this is, so the idea is instead of doing the full-fledged optimization in the dual, you only take one coordinate and you take a step. Now, it turns out that if you just take one coordinate and take a step, this more or less becomes an analytic function. Okay, so you can sort of write the exact equation. If you write the exact equation, you can show that every time your gap is reducing by a certain amount. Okay. So, while this is all these symbols are sort of very intimidating, the key idea of why you can show that your gap is decreasing is roughly intuitively because your dual is a quadratic programming problem. Okay. So, which means that if you look at it at any direction, it looks like a quadratic function. Now, if you have a quadratic function, you start from a certain location, you can more or less say, if I take a step in that particular direction for a quadratic function, you can more or less work out how much decrease in the function you will get, right, because it's a quadratic function, you know everything about it. I mean, you learned it in high school, right. So you can tell me exactly if I take a step, how much will I at least gain. So what is happening in these methods is that the key is you can always show that in your dual you will make at least some progress. Okay, so this is the intuition behind the proof, that you can always show that you will at least make some progress. But you have to remember that the proof is sort of horribly inefficient. And it's like completely inefficient because here you have a t-dimensional optimization problem. You say, oh, this is hard, I cannot do anything about it. So what am I going to do? I am going to completely cheat and take a one-dimensional objective function. It's like, I'm completely chicken, t-dimensional optimization, I can't do it. But one dimension I can do it, right. So for a one-dimensional objective function, so you are sort of saying the improvement that I would get in the dual by solving this problem is at least as much as sort of solving a one-dimensional problem. This is like, this is like a very bad proxy. And even then you can show this kind of a result that your bounds are actually, your gap is decreasing, and therefore you can come up with rates of convergence. Okay, so you just have to do induction. But the reason I bring this proof up is for two reasons. This is a fairly common trick. So if sometimes you are trying to prove convergence of some of your algorithms, this is a very good trick to go into the dual and sort of do this one-dimensional optimization. The other reason is I want to point out that this is a very inefficient way of doing the proof. But again, we will show that the bounds are tight. Okay, so it's even though there seems to be some kind of inefficiency in the proof, I will go ahead and show you that actually the bounds cannot be improved. Yep.
So I guess I'm a little unsure. What is the one dimension that you're picking out?
So you take the latest dimension that you added. So you see, because at time t you're solving a t-dimensional optimization problem. So because see, this is your piecewise linear function. At every time you add one extra piece, so the t keeps growing. So when you have one extra piece, sort of the dual is growing by one extra dimension every time. So at iteration t, it has certain number of variables. At the next iteration, it has one extra variable, right? So and then the piece that you choose actually is just the last piece. The newest subgradient that you added has a dual variable, and you only optimize that dual variable.
Okay, but somehow that doesn't get you in trouble the way that actually using only the last subgradient would.
So what we are doing is, I mean, intuitively, see, think of it this way, that for every one of these linear pieces, there is a dual variable here, right? So what we are really doing in the proof is saying we sort of keep the rest of the previous pieces fixed and just optimize with respect to the new piece. So it's a sort of a dumb strategy, but it gives you enough to show that the dual progress that you'll get by doing this dumb strategy is at least as good as the dual progress that you'd get by doing this clever strategy. That's the idea. Okay. Questions? Good. So now let us, and sort of this is a plug, but again just to give you some context, the best known rates that I know of for bundle methods is roughly order 1 over epsilon cubed by QVL. But in our case, you have to remember that the solver that we are using is a specialized solver, right? So it is not a general purpose black box. You cannot throw a general purpose black box objective function at it. It has to be a regularized risk minimization problem. So therefore, you can actually get better rates of convergence. There is a, like I told you, this proof has been invented and reinvented a few times in machine learning. So there is, our proof actually improves the rates of this paper. Some of you may have read this paper called structural, it's called structural support vector machines, or this is the paper which introduced, some of the structured learning stuff that Dale talked about. And their rates of convergence are order 1 or epsilon, and it turns out that we just do a slightly refined analysis and that gets 1 over epsilon. So that was sort of, so if you really like your epsilon deltas, and this is a good nice industry to be in if you want to write papers.
What is the sort of state of the art in the optimization? Like what is defined as, so the superiority of methods are measured by epsilon, or?
Yeah, so you always ask for, the way you compare different methods is you ask for a given accuracy epsilon, how much steps or how much time will a method take, right. So, in this particular case, so for smooth objective functions you can get very, very good, like you can get log 1 or epsilon or log 1 or epsilon, but for non-smooth functions this is more or less where you are stuck. Okay.
And these are all still identifiable?
Sorry?
And it's still identifiable, like if you were to grab that state of the art, which is much slower,
Uh-huh.
and ask for the same epsilon, and then grab yours, which is faster, and grab the same epsilon, will you get the same weights?
Yes. So, okay, here you have to be very careful because you are working with non-smooth functions. So, there is always this issue that I can tell you that the gap is below a certain threshold, but I cannot tell you that the solutions that are produced will be exactly the same, okay, because of numerical issues. Okay. And even in a smooth objective function, I can only tell you that they will be exactly the same within numerical precision, right, and that's always the caveat. Other questions? Good. Yep.
Probably I'm not understanding correctly, but if epsilon is less than 1, then isn't that like a worse rate of convergence for 1 over epsilon cube?
Oh, 1 over epsilon cube is a horrible rate of convergence, right? More or less it's a really bad rate to converge at. 1 over epsilon is already a pretty bad rate to converge at. What you ideally want is log 1 over epsilon, and even better if you can do it log 1 over epsilon. Okay, so I'll show you Quasi-Newton methods which get you log 1 over epsilon, and then limited versions which will get you log 1 over epsilon. Okay. These are, I mean, this is sort of, I'm just showing you the proof. There are a couple of reasons for it. One is I just know that this happens many times in machine learning. So hopefully if some of you are masochist enough that you want to prove some convergence bounds for any of your algorithms, some of these techniques may be useful. The other reason is I want to show you later when we do the lower bounds, I want to show you what happens with those lower bounds. Okay. So let's quickly run through the experiments. Okay, I don't want to bore you with the details. Again, you can go and look up. The code is available online on my students' homepage. So if you go to Chunhuitio's homepage or just type in BMRM in your favorite search engine, you should be able to find the code. You can download, play with it. We are trying to get a better release done at some point of time, but right now what you have still more or less works. Okay, but I want to show you something very peculiar that happens in the experiments. Okay, and then I want to motivate the lower bounds. So the peculiar thing that happens in the experiments is the following thing. You go and download, you go and run your this solver on a standard problem. So some RCV1 problem which has about 50,000 dimensions, about 670,000 examples. Okay, and just do binary classification. This is the rate at which theory predicts that your optimizer should converge. Okay, and this is the rate at which your optimizer actually converges. Okay, and this rate is actually log 1 over epsilon. Okay, so your theory says that your optimizer should converge at order 1 over epsilon. In practice, it converges at log 1 over epsilon. What's going on? Same thing, similar thing happens in a different data set. So that if you go through a number of different settings, again I don't want to bore you with the settings, but more or less all the time we somehow empirically seem to observe that we get log 1 over epsilon rates of convergence, while theory predicts that the optimizer converges at 1 over epsilon, right. So this was a problem that was very intriguing. I mean, it was stumping us for a long time, and I thought, oh, maybe because we are not doing the analysis right. You remember we are doing this one-dimensional thing which is a proxy. Maybe the analysis is so horribly loose. We could get from 1 over epsilon square, we could tighten the bound to 1 over epsilon. Maybe if we did something more cleverer, we would get log 1 over epsilon. Right? So for about 1 or 1.5 years, I kept on asking my students, this doesn't sound right, this doesn't sound right. Why is it that the optimizer converges at log 1 over epsilon on practical problems, while theory predicts that it should be 1 over epsilon, right? Maybe our analysis is not right, maybe we can improve our analysis, maybe we can do something. It turned out actually, and this is rather surprising to me personally as well, is that you can show that the rates of 1 over epsilon are optimum. You cannot improve them. So the way you show these rates is by constructing an adversarial setting where you show that you can ensure that your optimizer would take order at least omega 1 over epsilon iterations. Right? So so the way it is done, this is work that I did with my student Xinghua Zhang and Angkhan Saha. Angkhan is not here, but he was here last week. So what you do is you come up with this, you cook up this binary classification problem. The binary classification problem that you cook up is, first of all, you come up with the dimensions which depend on the epsilon that you need. So you say, okay, if I want to get a certain epsilon precision for my lower bound, then my dimension must depend on epsilon. Okay. Then you have data points. Every odd point is labeled -1 and every even point is labeled +1. Okay. And your instances look somewhat weird. So the first coordinate of every instance is square root m. Okay. And the I plus 1th instance, I plus 1th coordinate of every instance is m. Okay. And everything else is 0. And then there is a sign pattern which is determined by whether it is the odd or the even. Got it. If you write your binary classification problem here, you can immediately see that the loss only depends on the first coordinate of your weight vector and the I plus 1th coordinate of your weight vector, right, because there are only 2 guys which are non-zero here. So therefore your loss only depends on these 2 guys. Okay. And this is a rather simple problem. You can more or less calculate what the minimizer will be. Right. So the minimizer basically has some term which is depends on m, and then all the other terms are non-zero and they are identical. Okay. And you can also compute what the exact value. So this is a really simple problem to set up. But the fun thing is you can show that after t steps of your algorithm of running this BMRM algorithm, the weight vector that you will obtain will only contain the first t plus 1 coordinates will be non-zero. Everything else will be 0. So which means that you are very far away, because all these guys are non-zero in the final solution, but your tth solution, all of them are 0. So intuitively you are very, very far away. Okay. Again, the details are sort of in the devil is in the details. You really have to sit down, work out all these things, work your epsilon deltas carefully, but you can show that you will converge rather slowly. So you will need at least 1 over epsilon iterations before you reduce your gap down to epsilon. Okay. So this brings you to this sort of philosophical question, which is, what does it mean when you are proving upper bounds and lower bounds for these optimizers? Okay. So you have to understand there is a very, very subtle things going on here. What does an upper bound guarantee? And of course this is a question that I keep getting asked many times is, oh, but you showed that the optimizer converges at log 1 over epsilon on practical problems. So does that mean that it violates the lower bound? The answer is no. So let's see why. What does your upper bound guarantee? Right? So this is again a little bit of parsing of math, but let's do it. So your upper bound guarantees that there is a constant such that whatever epsilon that you give me and whichever function you choose from this function class, the number of steps that my optimizer takes to get an epsilon precision solution on this function is at most some constant times 1 over epsilon. Right? So this is what my upper bounds guarantee. So you give me any arbitrary function, I will give you an epsilon accurate solution in 1 over epsilon, at most 1 over epsilon steps. On the other hand, the lower bound guarantees that you fix an epsilon, okay, then I can give you a constant and a function which belongs, a bad function which belongs to a function class, such that your optimizer requires at least 1 over epsilon steps to get an epsilon accurate solution on this function. Okay. So it says there exists a function which is bad. That one says for every function it is at 1 over epsilon. Right? So this is so all playing around with existential and for all qualifiers. But sort of this is a picture which tries to describe this in a very naive way, is to say your landscape, so let us say this is just some weird landscape where what I am plotting is the time that is, so your axis is the set of all possible functions, and for every function I am plotting the time that the optimizer takes. Okay. It might be that for most of the functions the optimizer takes very small amount of time, but there might be some functions, some really bad functions, for which it takes a lot of time. Okay, we do not know this. So maybe we need to do more refined analysis, maybe we need to do something like the smoothed analysis. So for those of you who know about the simplex algorithm works extremely well in practice, but you can show that it is exponentially bad. Okay, it's a similar situation here. So BMRM works extremely well in practice, but you can show that the rates of convergence are tight. So in other words, there is no hope that somebody can come in and do a slightly better analysis and say, hey, you could get better rates. This answers the question. And just to give you some references, there is a paper on the lower bounds which appeared in NIPS 2010. There is a paper on the bundle on BMRM and all the details of the convergence proof that appeared in JMLR 2010. We did the convergence analysis first at NIPS 2007, and we presented the solver for the first time in KDD in 2007. Okay. Yep.
Can you say a little bit more about how the runtime typically compares with other optimization methods?
With other
optimization methods?
So if you look at anything else, I didn't plot the other ones, but if you look at any other normal standard bundle method, we are much faster.
Well, how about actual runtime, seconds?
This is actual runtime. Well, this is iterations versus approximation time. I don't have the figures here, but in runtime we are actually faster than most of the existing methods. So it's not just in theory that we have better rates, but also, so we are better than S.V.N. perf, but more or less so we are a slightly more general formulation and our solver is slightly more general, but for quadratic regularizers we more or less become the same as S.V.N. perf, but we have a slightly better implementation, so we are slightly better than S.V.N. perf in terms of convergence. In terms of normal bundle methods, they are nowhere near us. We are much faster than normal bundle methods. There is also another thing to keep in mind is that the lambda plays a big role. Right? So more or less if you give a large value of lambda, every optimizer and its dog will converge to the right solution. Right? The real fight is when lambda is very small. That is when sort of the non-smoothness really matters, and then it separates the good optimizers from the bad ones. Yep.
So were those kind of like worst case lower bounds then? That the idea that in the worst case it's always going to be 1 over epsilon, but it turns out in a lot of cases, or at least some of these.
So that's why I said the lower bounds simply say there exists a bad function. They don't say that for every function it is bad. Right? So that's why it's sort of very important to read this in the right way. There exists a bad function, while that one says for every function there is an upper bound, and this says for some functions that upper bound is met. Okay? But for this is my conjecture that most of the cases we are actually pretty good. Okay? And it seems like most of the practical cases we are right here. Okay? Yep. Which one? These you mean these yeah, but sure, I mean similar, yeah. Again, I mean I'm simplifying the lectures quite significantly, right? I mean I'm trying to concentrate on one thing and show you one thing, but if you go to my homepage, I have some talks, and also you look up the paper or you download the code, play with it. Other questions? Okay, good. Now let's go on to my next talk. On Quasi-Newton methods. Questions? Do you want a minute to stretch yourself? Just a minute though. Don't leave your places. Let's just all, let's all do straight. Okay, good. Let's get started. Okay, so since I don't want to overrun into the break, so let's try to do this. So what I'm next going to talk about is Quasi-Newton methods. Okay, so what are these V's and where do we stand? So let's first take a step back and see where do we stand in this whole spectrum of things. Okay. So of course our aim is always to do regularized risk minimization, and prototypical example that we are using is a linear S.V.N. Okay. So what we saw in the very first lecture, the very first day on Monday, was we looked at online algorithms, right? So and also Leon dwelt extensively about online algorithms, stochastic gradient descent, second order stochastic gradient descent, and so on. The philosophy there is that you use only a small subset of the data at every time, and then you repeatedly cycle through your data. So these are the online learning algorithms. While what we saw in the first lecture is an example of a batch optimization algorithm, which means you assume that your entire data set is available to you in one shot. You take your entire data set, you evaluate your function, you evaluate your gradient, and you keep on doing your optimization. Okay. So we looked at this one. We'll come back to something which is closely related to online learning algorithms if I have time later in the lectures. But now we are sort of in this mode, in this batch optimization mode. Okay. Now there are two fundamentally different philosophies on how you can use your gradients. Okay. So how can you use your past gradients? So we saw one philosophy, which is what the bundle methods did, which is you use your gradients to lower bound the objective function, right. So you build a piecewise linear lower bound, you know how your function looks like, you know that your function cannot go below this value, and so on and so forth, and you use them. Okay, clear? There is a different, almost a different school of thought or a different philosophy, which is, can you use these gradients, and the question they ask is, can you use these gradients somehow to come up with an quadratic approximation to your objective function. Right. So in other words, instead of a piecewise linear function, you say, can you say locally this is how my function looks like, and can you come up with a quadratic approximation? Okay. So that is the kind of algorithms that we are going to study now, these Quasi-Newton algorithms. Okay. And for those of you who know a little bit about Newton algorithm, about the Newton algorithm for optimization, these are basically the Quasi-Newton algorithms are trying to do something similar to the Newton algorithm, except that they only estimate the Hessian. So we will see these differences in just about a minute. Okay. Before I go, how many of you know or have heard about the Newton algorithm? Good. And how many of you know what the Newton algorithm exactly is? Can you like write the equation right away? Good. Okay. So okay. So Quasi-Newton algorithms, let's first do again the same way like we did for bundle methods. The way we are going to do it is we are going to look at classical Quasi-Newton algorithms, and then I will show you how where they run into trouble when you work with non-smooth problems, and then I will talk about how you can fix them, particularly for the cases that we are interested in. Okay, and then I will show you some experiments. So this is a very rare picture, and there's a remarkable story behind, which goes behind Quasi-Newton algorithms. Okay, so let me maybe spend some time telling you this story. So if you use any standard package like MATLAB, R, Python, any of these, and you call fmin or function minimizer or funcmin or whatever it is called, okay, the default convex or even non-convex function minimizer. Okay. By default, at least as far as I know, they all call a algorithm which is called LBFGS. L for limited memory, and BFGS stands for these four gentlemen. Okay. Okay, so that's Broyden, Fletcher, Shannon, and Goldfarb. Sorry, Goldfarb and Shannon. Okay. Yep.
Is it the same Fletcher as from Fletcher-Reeves?
Sorry.
Is it the same Fletcher?
Yeah, it's the same Fletcher from Fletcher-Reeves. And Broyden, more or less, his entire career has been on BFGS type methods. Shano did other things. Goldfarb also did a lot of other. I mean, Goldfarb is also very, very well known in optimization. Okay, and so they, all four of them, and this is actually a picture. Sorry, I forgot to add the credits. I should add them. The picture is from Dennis' homepage. Dennis is also one of these big optimization guys, and this is a very rare picture of all four of them exactly lined up like this. So it turned out in 1970, in 4 different journals, almost simultaneously and completely independent of each other, all 4 of them came up with exactly the same algorithm. Okay. This is remarkable because when you see the algorithm, and there is this one place which is voodoo black magic in that algorithm, and to me, I still cannot fathom how all 4 of them came up with exactly the same black magic at exactly the same time. So this is kind of, and those were the times when the probably, you know, archive and optimization online did not exist, so probably they didn't get a chance to see each other, like see what the others were working on, so probably they just ended up reinventing the same algorithm. So it's named after them. Actually, to be fair, Broyden had the broadest class of algorithms. So he sort of defined the broadest class of algorithms of this kind. Okay, and that algorithm from the 1970s was improved by Nosidal in 1994, where he came up with what is called a limited memory version, which is what is used in your machine. So if you really call function minimization, funcmin, on your computer, then more or less you're calling LBFGS. And then Bala will tell you another story about how there is a whole, it turned out that some people did not like it being called a BFGS algorithm. So there is a whole group at Aragon which completely always insists on calling these algorithms LMVM algorithms, which is limited memory variable metric algorithms, but they're exactly the same. So if you see an LMVM algorithm, that is nothing but a LBFGS algorithm. Okay, so except that it's most probably being written by somebody at Aragon National Labs. Okay, so anyways, this is the story. Now let's actually look at what these guys were doing. Okay, so if suppose again the standard assumptions that we make, we are given a convex function, we know its gradient, you know, and we can evaluate the function and the gradient at any point. And for the first part, for when I'm talking about Quasi-Newton algorithms in the beginning, everything is differentiable. Okay, so smooth differentiable, nice functions. So you get a smooth differentiable function. Before, you remember what we were doing is we were making a first order Taylor approximation, right? So we did not have this term, we are just making this approximation. Okay, so now we are evolving a little bit more, becoming smarter, and we say, oh, we know Taylor expansion, so let's do a second order Taylor expansion. Okay, so if you take a second order Taylor expansion, and if suppose this HT were the true Hessian, then this is the second order approximation to your function, right? So to your function j. So you're given an objective function j, you make a second order approximation to it. So a second order approximation is simply saying, sort of, from among all quadratic functions, tell me which is the quadratic function which locally fits the function the best. Okay, clear? Now you have this sort of local model of how your function looks like, and what you can do is you can minimize this model and come up with a solution. Exactly the same like what we did before in bundle methods. In bundle methods we made a piecewise, in cutting plane methods we made a piecewise linear lower bound to the function. Here we have a quadratic model of the function, and we are minimizing it. Okay. If you minimize this, take gradient, set it to 0, pretty elementary stuff, you will get an update which looks like this. Okay. For those of you who forgot Newton update, this is the Newton update. So basically you take your current parameter, you take your Hessian, you invert your Hessian, multiply it with the gradient, and you take a step. Of course, for any good person who does a practical implementation of Newton would not believe the Newton direction completely, so you would always do a line search. Okay, so you always say, okay, I get this Hessian inverse times the gradient, and I am going to do a line search along this direction. Okay. Now the difference between a Newton method and a quasi-Newton method is that in a quasi-Newton method you do not use the true Hessian. Okay. Instead of using the true Hessian, you use an estimate of the Hessian. Okay. So you say, let me try to figure out what the Hessian is, let me not compute it. Why would you do that? Any guesses? It's very expensive to compute the Hessian, right. So if you have a d-dimensional optimization problem, every time you have to spend d square effort to compute the Hessian. Once you have d square effort to, so if d is very large, which is typically the case in machine learning, like for instance if you are dealing with RCV1, you have 50,000 dimensions, you cannot even store a 50,000 by 50,000 matrix in your machine, right. So how are you going to even optimize it? So this is the reason why a quasi-Newton method sort of cheats, and it says, okay, instead of actually using the true Hessian, I am going to approximate the Hessian. Okay. And this HT is basically the approximation to the Hessian. So before 1970, there was another algorithm which is called the David and Fletcher and Powell algorithm, DFP for short, which used to do this, and it was reasonably successful, but not as widely successful as BFGS. Okay. The reason for that, can anybody think of what could be the reason why that algorithm was not very efficient? Well, the problem is that you come up with an estimate of the Hessian. If it is a d by d matrix, you have to invert the Hessian. If you invert the Hessian, it is an order d cubed operation, right? Very expensive. So that is why this algorithm, although I mean it existed before 1970, was not very popular. Or yep. You can handle the degeneracy of the matrix by doing a CG solve. So actually that's another thing, you should talk to me in the break. If ever in your life you actually computed the true Hessian, true inverse of a matrix, then you need a remedial course. You need to come and talk to me. Okay, and if you ever in your life plan to compute the true inverse of a matrix, then again please come to me before you have to take the remedial course. Okay, so you should never invert a matrix. Yeah, you had a question?
How can you ensure that Riccian exists with second order derivatives?
So I am assuming here that the function that I have is smooth and differentiable. For Newton, I need to assume that it is also twice differentiable, but here since I am only estimating the Hessian from the gradients, so I do not need twice differentiability, but I do need once differentiability. So I need C1 functions. Yep.
Just to never invert the matrix, this might not be related, but doesn't sometimes inverting the matrix give you statistics about your weights?
You never, so the way you solve this is you never, okay, so maybe I should write this since this is important. So if you have a matrix A, right, and one of the main reasons you would want to compute the inverse of the matrix is because you want to do something like A inverse and multiply it with B, right. So like in this case you have the Hessian inverse the gradient, right. So this is what you want to do. So every time you have a matrix A, you want to invert it and you want to multiply it with a vector like this. There are two ways to do it. Okay, the sort of naive way to do this is you take A, you run your MATLAB inverse on A, right, and then you take star B. Okay, and this is a strict no. You do not want to do it because the inverse is numerically unstable. Not only that, this is an order d cubed operation, okay, and also numerically unstable. The way you want to do this is as follows. You want to solve the following system of equations. You solve this guy, and this you can solve by something very, very useful, which is called a CG solver. So, a conjugate gradient solver. So, if your matrix is positive semi-definite, it works beautifully. If your matrix is not positive semi-definite, you have to do some kludge on top of it. But this is how you compute A inverse B. Clearly, as you can see, x is equal to A inverse B. Right? So, this is how you compute A inverse B. You never solve. Yep. Yes, yes, yes. Very, very good library. Very, very recommended. It's called PETC. It comes from the Argonne National Labs. Yeah.
If it's positive definite, why CG and not Cholesky?
You can do Cholesky. So if you want to solve the system many times over, then you want to do Cholesky. But if you want to do a one-shot computation, you want to do CG. Because Cholesky is order d cubed work, while CG is only order d square times the effective rank.
So when you do the / is that called CG, like in MATLAB?
Sorry, when?
A/B?
I don't think it calls CG. I don't know, maybe it has gotten smarter, but usually it was pretty dumb before. So I think it used to compute the inverse and then solve it, but I don't know it.
A/B is it's a lot more computation efficient, but I don't know why.
Oh, so you're saying A minus / B? You mean A like minus / B? Yeah. That does a CG solve. Yeah, you're right. Yeah, that does a CG solve.
I guess it's using theoretical position.
It depends internally what they do, but again, MATLAB is something that I haven't used for ages, so I can't tell you exactly what they do.
What is the reason of using inverted Hessian here?
For using the inverted Hessian, if you take this, so if you take this model, you take the gradient with respect to W and set it to 0, you will get this equation.
Yeah, but why?
What do you mean why? Sorry, I don't get your question.
If you update, for example, you try to optimize some functions by gradient.
Yes.
So you make the derivative of some function, right? Because when we go by directions, by gradient directions, we go somehow to the local or global.
Yes.
So here, why we use it?
So see, what you are doing is you have, so what you are talking about is just doing gradient descent, right? So you just take a gradient, take a step in the direction of the gradient. These are slightly more sophisticated algorithms. They make a local model of how the function looks like, right? So they say, okay, locally I want to find out how does the function look like. So the way they do it is they build a quadratic model. If suppose, pretend for a minute that your function was twice differentiable. Okay, so it is twice differentiable. So the Hessian, the HT is actually a true Hessian of the objective function. Okay, so if HT is the true Hessian of the objective function, this is nothing but the second order Taylor expansion. Okay, so the second order Taylor expansion is like a second order approximation to your function. Correct? And now to take a step, you minimize your second order Taylor expansion. This guy, if you minimize this, basically you take gradients and set it to 0, you will get this update. Now the only difference is that instead of using the true Hessian, I am going to approximate the Hessian, but my update still remains the same. So this is basically nothing but the Newton update. If this HT were the true Hessian, this is the Newton update. Okay, clear? Questions? Yeah. Okay, so let's come back to let me take 2 minutes more and then leave you with some things to ponder about, and then we'll come back to it. Okay, so here is sort of the classic thing that I tell my students, that by changing one symbol you can become really famous. Okay, so here's a classic example of this. So the DFA algorithm was around for a while, but it was not very popular because it was using the Hessian and it was inverting the Hessian, right? The order d cube operation. These guys, Broyden, Fletcher, Goldfarb and Shano came, looked at it and said, wait a minute, we are just looking at approximating the Hessian, right? So we are sort of getting an approximation and then we are inverting the approximation. Doesn't seem right. Why don't we do the following thing? Why don't we directly approximate the inverse of the Hessian? If we are doing an approximation anyway, why don't we just approximate the inverse of the Hessian? Now the moment you approximate the inverse of the Hessian, lo and behold, there is no inverse in your update equation. So this is just a simple matrix vector product, okay? So and then that's a line search, and there you go, okay? And this is what basically revolutionized optimization, okay? So think about it. We'll come back and talk a lot more about this algorithms after the break. Thank you.